Welcome to the presentation on retrofitting urban stormwater system with green infrastructures. And I am Soilud Sakya, and this is our presentation on final project, which is a requirement of the course CEE 750 Urban Runoff Quality and Control. Let's get a quick overview of what we will be going through on the presentation. So first we will be looking at the introduction, the objectives of the project, the study area and its properties, the site and the layout of the stormwater system, the data that we will be using for this modeling, the parameters that we will be using for the models, and the calibration, how we are calibrating the model, and we will look at the sum of our results, and then we will conclude. To begin with the introduction, stormwater has been managed by quickly rejecting the runoff from the site to the drains. So as an example, there used to be a vegetation in the area, and then we constructed the impervious cover on it, and because of that this alters the balance in the natural infiltration, because the rainwater cannot infiltrate into the ground. Also the runoff is increased because of that, and it gets collected in the natural channels, and then this creates the whole problem of flooding in the natural channels, erosion in the channels, also early picking in those natural channels, and then we will have low base flows. So the objective of this study is to reduce the runoff quantity and the pollutant loads. So we will be looking at three of the pollutants, which are total suspended solids, TSS, lead, and then polyaromatic hydrocarbons, PAHs, which are the output of the comes from various sources, such as the smoke or the petroleum products, and also sealants, etc. So we will be looking at the runoff quantity and the pollutant loads from the study site by retrofitting the existing structures with green infrastructures or low impact development controls, LID controls. So we will be interchangeably using the green infrastructures and LID controls to demarcate the retrofitting that we are doing in the site. The LID controls that we are looking at are permeable pavements, infiltration basins, rain cisterns, and rooftop disconnection. The existing stormwater drain network will be modeled in SWIM, which stands for Stormwater Management Model, with pollutant built-up and wash-off parameters depending on the land use. And we will finally analyze the effectiveness of those LID controls and also cost of the retrofitting of the subcatchments. The study area is inside the premises of the University of Nevada, Las Vegas, and covers 57 acres and drains to the junction in Maryland Parkway and University Road. And this is the southernmost part of the premises of the university area, and this area has more than 10 parking lots including a garage, and has buildings with large footprints and is susceptible to flooding in storm events. Let us quickly jump to Google Earth and see what we are trying to do. So the yellow polygon is showing the whole UNLV premises, and the small polygons in this area are the subcatchments that we are trying to analyze. So we will shortly see that the hydrological analysis of the whole area is in such a way that this area drains independently and also has an independent stormwater network and drains to the junction, which is in the Maryland and then University Road junction. The study carried the hydrological analysis of the area with a digital elevation model, which had a resolution of 1/3 arcsecond, and this was analyzed because we wanted to see how the area of the UNLV is behaving hydrologically, and we found out that there were 3 independent stream formations by the process of stream ordering, and we can see that the southernmost part behaves as an independent hydrological catchment, and this is why we are selecting only the green part, which is in the southern part of the UNLV campus. So this is the area that we are looking at, and these are the subcatchments that are formed on it, and these are the names as it is on the actual site. Like this is the north black lot, this is the south black lot, and UTC, which is the transportation area, and So these areas are named on the basis of the location. So these subcatchments are formed based on digital elevation or the DEM and the existing structures. For example, this area, which is the SR Tropicana Garage, is a independent roof, and it drains to the inlet that is present in it. We have to treat this area as an independent subcatchment, and similar goes with the resident lot B, which is also a parking lot, and there are inlets, and so we are decided this the whole division of the subcatchments on the basis of existing structures, the stormwater inlets, and the DEM. So we identified 22 subcatchments in the area. This is the layout of the pipe that is existing, and it consists of 44 junctions, which are the nodes, and 44 conduit links, and one outfall at the Maryland Parkway and the University Road. And the existing stormwater drain networks was replicated from as-built drawings, which was obtained from the facilities management of UNLV, and the conduit size, length, the invert level of the junctions and manholes were used along with the location of this element, and we verified these locations using AutoCAD as well as Google Earth, so in parallel, so that we can verify all of we are doing the correct layout. Rainfall data was obtained from Clark County Regional Flood Control District website using station ID 4484. And we can see the location of the station, which is within the premises of the UNLV, and we are using 6-hour duration rainfalls, which has a return period of 2 years as well as a return period of 100 years. So we will use the 6-hour duration rainfall with a return period of 2 years for calibrating the event mean concentration of pollutants we will try to calibrate the EMC with the similar studies that was conducted in the same UNLV premises, and also we'll use the 100-year return 6-hour duration rainfall for identifying the flooding nodes, as well as trying to retrofit the area to stop the flooding and also reduce the pollutant loads. We use the flat slope 2% low runoff type soil and soil drainage of 1 inches per hour for the stormwater calculator, and this is used because we are interested in finding out what percentage of the precipitation turns into the runoff, so that we can calibrate the volume, which we will see shortly. So we have seen in the previous slide that we divided the whole area into 22 subcatchments, and then the area, perimeter, and then flow width of these subcatchments were calculated using the ArcMap, which is a GIS software, and we also calculated the percentage imperviousness of each of the subcatchments using supervised classification and NAIP high resolution imagery, which stands for National Agriculture Imagery Program and has a resolution of 1 meter. So this is an image of the whole UNLV, and the area is classified into 5 classes: blacktop, grass, barren, roof, and trees, and we will classify them into pervious and impervious, and which will be used as an information to the model. So this is the table of the information about the subcatchments that we will use, and there are 22 subcatchments. As you can see, the area of these subcatchments, which the highest area is 11.94, and the percentage imperviousness that we calculated from the supervised classification, the width of the subcatchments, and then the slope is calculated from the DEM, and the percentage of vehicle land use is based upon the what percentage of the land is accessible by the vehicles. For modeling of the pollutants, we divided the whole area, as we are saying, that into vehicle and then non-vehicle, which means the areas can be either accessible by vehicles, and then we will call it vehicle because it will have different pollutant loadings built up and wash ups, and Also the area which are non accessible by vehicles will be categorized as non-vehicled. We will for the total suspended solid, we will use the power function for build-up equation, which is given by this equation, which means the minimum of C1 and then C2 times the power of T to the constant C3, and the constants are calibrated or iterated on the basis of the final concentration on the outfall, and we iterated the study iterated for multiple times, and we found out that these constants works so that we will get the correct or within the range concentrations. We will also use the event mean concentration EMC for the WASOF, and this value comes from the similar study which is from Acharya et al, as we will see in the calibration part. And lead and PAH, which are the other two pollutants we are looking at, will be modeled by using the cofraction of TSS, which means a certain fraction of TSS, and this is a common method because TSS is very good surrogates for many of the pollutants, including lead, heavy metal as lead, and also PAH. Let's go to the calibration part of the model, and we are calibrating the total runoff volume at the outfall based upon the runoff percentage that we obtain from the stormwater calculator, and we are using the precipitation depth times the area times the runoff percentage, and then we estimated that 0.6 million gallons of water has to be collected if the model is working well, and for the 0.7 inch of rainfall of 6-hour duration. So this was made true. And also for the pollutant loads, TSS we calibrated on the basis of Acharya et al, the monitoring study by Acharya et al 2010, and then also there was an other study, a thesis written by Malik et al 2008 for the quality. The event mean concentration of WASOF of the pollutant was assumed constant for 490 milligrams per liter, and as which is observed in the monitoring study in the Acharya et al 2010, which is conducted in the UNLV premises, and so we are trying to keep it consistent with the previous monitoring studies. For the pollutant loads, leads and PAs, the literatures were referred, and the lead was assumed to be 0.0005 cofraction of TSS, which is in terms of per liter, and PAs is lesser than that, which is 0.001 cofraction of the TSS. The concentration of TSS, lead and PHS at the outfall are expected around the national survey data of EPA, which is the table that we can see in the right side. The TSS has to be within the 180 to 548, and from the literatures we found out that for arid climate the TSS is usually higher than the national average, and for the lead it has to be around 182 to 443 micrograms per liter, which is 0.1 to 0.4 milligrams per liter. We are so this results, this LID control sizing is based upon the iterations. But the drainage cisterns, we are using 3500 gallon PVC cisterns, which has a diameter of 7 feet and a height of 12 feet. It's a cylindrical vessel. Similarly, the infiltration basins are 80 feet long and 20 feet wide, which can be placed in the parking lots so that they can function as a parking spot when the rainfall event is not happening, as well as infiltration basins when the rainfall occurs. And the permeable pavements, and then just rooftop disconnections, this depends upon the site, and we will shortly see. So the LID control modeling, we have different layers depending upon what kind of LID type we are using. So typically there we can identify 3 layers, and for the infiltration trench there is a surface layer, storage layer, and optional drain layer. For permeable pavements there is surface layer, pavement and storage, and optional soil and drain. For rain barrel there is only storage and drain, and rooftop disconnection there is surface as well as drain. So these parameters has to be defined in the model so that we are doing the practical values. For permeable pavements, the surface Manning equations, the Manning constant is assumed as 0.02, which is typical for the concrete, and the 1% slope for pavement, the thickness is 6 inches, soil 36 inches with a weight ratio of 0.15, for soil is 0.5 conductivity inches per hour, and the storage layer is 18 inches and with a seepage rate of 3.5 inches per hour, and has a drain flow coefficient of 0.5, which is for the orifice flow. And as we can see that we are assuming the orifice flow for drain system as well 0.5, and as well as infiltration basins. For rain systems, we are assuming as we say that it's 12 feet high and 7 feet in diameter cylindrical cisterns. For rooftop disconnections, we assume that the storage depth is 3 inches and the Manning equation 0.01, Manning's constant 0.013, which is for the corrugated sheets or roof, and the flow capacity is 6 inches per hour for the drain. And for the infiltration basing, the Manning's equation is assumed at 0.1, which means it's a rough surface because of the presence of the pebbles and the gravel, and also the storage is 18 inches with the seepage rate of 0.5 inches per hour, and the flow coefficient, as we said, that the orifice for 0.5. We can also see in the visuals like how the pavement layer, soil, and then storage are functioning as the rain falls and it penetrates, and then we get the drain when it's extra, and then the rest of it infiltrates. Moving forward, the efficiency of the LID controls needs to be defined so that we tell the model what percentage of the inflow pollutants are captured by the LID controls. So we assumed based on the literatures, as from the literatures, the removal for the all the pollutants, DSS, lead, and PHS is removed 50% by permeable pavements, 20% by rain cisterns, and then 75% by infiltration trench. So this is coming from the literatures, and let's go to the model simulation. Let me minimize and then open up my model for the existing pre-development condition. So this is the total area that we are analyzing, as we saw, and this is the pre-developed condition, which means the whole area is drained towards the outlet, and this is the rain gauge which has different rainfall, and right now we are considering only the 100-year 6-hour duration rainfall. So let's run it and see that there is very less continuity error, and if we go to the summary reports, then we can see how much total infiltration is happening, and then how much wash of the TSS, lead, and PAS. We will summarize this in our slides in the end. Nevertheless, let's go to the other model, which is the existing model without the LIDs, and this is the model. So we can see that we have 22 subcatchments in place, and all of these links and the nodes are the information are coming from the data that we talk about. And let's quickly run this model, and just making sure we are using the correct rainfall, 6-hour duration, 100-year return period rainfall, and we will see that how flooding is occurring, or where flooding are occurring. And from the summary reports, we can see that no flooding is happening in 26 of the subcats nodes. And if we see the profile, so we will select the farthest end and then outfall, and then find the path, and then we will be able to see. So I'm running this for, so this is the 5 minutes of the rainfall event, and then this is the 10 minutes. As we can see, the nodes are already flooded in this the time step. In the 15th step, the more flooding is happening, and as we go, it's decreasing at first, and then another surge comes in, and we get again flooding in 26 of the subcatchments. To quickly show you, we are also getting the conduit surcharge, which means the pressure flow is happening in 34 of the subcatchments, and we can see that in this area the red is showing that the flow is more than 30 CFS. So let us go to the model with the LID in place, and this is done by let's see to the project and then hydrology and LID controls. And as you can see, we are using permeable pavements, roof cistern, which is the rain cistern, and roof disconnection and trench retention. So we have a mix of these LID controls in some of the subcatchments and only one or two of them in some of the subcatchments. For example, let's take this black slot south side. We have two LID control in place with permeable pavement as well as infiltration trench, and similarly let's look at this RWC, which is Recreation and Wellness Center, and the LIDs that are in place. So we click the conduit, so we are not getting anything. So if we go to the land use and then LID control, and then we can see that we are using roof cistern in this one. So we'll summarize what sorts of LID controls we placed in what subcatchments, but let's quickly run this model, and we can see the continuity error is very less, and we just making sure we are using the correct rainfall. And let's see if we got any flooding by seeing the status report as well as by more efficiently seeing the node flooding. So we can't see any node flooding, but we do have some secondary surcharge, which means we are getting some pressure flow, but we don't have any flooding. So we successfully removed the flooding from the pipe system that was already existing using the LID controls. And let's look at the profile first from the farthest end to the outlet or the outfall, and find the path, and then this is the 5 minutes, this is the 10 minutes, this is the 15 minutes, this is 20 minutes. So we can see that we were getting flooding in more than 26 of the nodes in our previous model without the LIDs, and now it's all under the control. So quickly going back to our presentation, so the flooding was occurring in 26 nodes and conduits such as in 34 conduits. So the application of the LIDs successfully removed the flooding in the nodes as well as reduce the pollutant loads. Let's see. So we use 92 rain cistern in 11 of the subcatchments, and this number are different, which we will see in this table, that in some of the subcatchments, for example day 2 and day 3, we see that we used rain cisterns in 6 numbers. Also permeable pavements were used in 7 of the subcatchments, which are primarily these parking lots and parking lots, and infiltration basins are used in 3 subcatchments, and 8 rooftop disconnection were used in 3 of the subcatchments, in which we had a mix of building as well as the open spaces, so that we can stop the flooding. So as we ran the model for 3 of the conditions in which pre-development condition without any impervious cover, or the natural conditions, the existing condition in which there were no LIDs but we had a lot of impervious cover with parking lots, and then footprint of the roofs that were constructed and the retrofitted in which we used the LID controls. We saw that from the model so initially in the pre-development condition, the runoff percentage was 20%, which increased to 57%, which is because of the impervious cover, and this was able to be reduced to 48% by retrofitting with the LID controls that we are talking about. And also we can see that infiltration was high, and now it's decreased from 79% to 40%, and then decreased to 47%. Going forward, we saw the reduction in runoff coefficients, and we see that in these subcatchments the runoff coefficient was 0.75, and then it got reduced to 0.15, which basically means the runoff is being decreased in each of the subcatchments. and this range from as high as 94% in case of black lot ash because of the use of permeable pavements, and the zero values are we are seeing are those in which we are not applying any LIDs. So this is a time series of the outfall, in which we are looking at the flow that is collected at the outfall, which is the inflow. So the upper part is the existing condition, in which we see that around about the peak inflow was 100 CFS, and then it's consistently high, which is higher than the inflow that we got in the retrofitted condition. And the another one is the total suspended solids, and we can see that the highest level is higher in the existing condition, and then it got reduced in the retrofit condition. But we can notice that the TSS concentration is relatively higher in the later part, and it's lower in the actual existing condition, and this is because we have a reduced flow, and because of the reduced flow the concentration is high, but we will see that the total amount of suspended solids that is collected or in the outfall is lower, which means we have trapped more amount of suspended solids. So similar results were obtained for lead, in which we can see that the peak concentration is lower for the retrofitted condition, and then the average concentration is reduced by the using of LIDs, and similarly we can see that the concentration for the PAH is around 0.05 milligrams per liter, which is around 50 micrograms per liter, and we can see the peak is lower for the retrofitted condition, and then this is because of the reduced flow in the that is coming to the outflow, because of which we are getting a little higher concentration than the existing condition. To summarize the outfall loading, we see that the average flow has decreased from 19.88 cubic feet per second to 2.57, which is a reduction in 87%. We also see that the maximum flow has reduced by 60% from 104 to 41, and the total volume is reduced from 2 million gallons to 1.1 million gallons, which is a reduction in 45%, and the total TSS is reduced by 55%, which was 3,583 milligram per pounds in the existing condition, and 1,527 at the present condition. And we can see similar reduction if 1.7 pounds of lead reduced to 0.7 pounds, and then 0.3 pounds of PAH reduced to 0.15. So the cost of the retrofitting was estimated by using the stormwater calculator, and for 3 of the LID controls. For a rooftop disconnection, we got an average cost of $65,000, and for the capital cost, which is the installment cost, and for infiltration basins, we got a higher cost, which is $27,000, and for permeable pavements it's even higher because it's in higher amount. Its use is in higher amount, so it's around $4.5 million, and the rain cisterns are estimated using the commercial websites, and then assuming a constant lump sum installation fees, and the cost is estimated to be $575,000, and the total cost of all the retrofitting amounts to $5.2 million, and for the maintenance cost it's amounting to total amount is $292,000. So concluding this presentation, the more flooding problem can be identified and then remediated using the SWIM model. The LID controls for creating green infrastructures are useful in reducing the stormwater quantity, as we saw, and also the pollutant loads. And the permeable pavements are highly efficient in urban areas with parking spaces, as in our case, and the infiltration basins are effective but could be constrained by space. Rain cisterns are useful in controlling peak runoff from the public buildings, in which we can't apply the the other kind of LIDs, and garages that has a larger footprint. And the final point note on this presentation is that we are not using any rain gardens or other bioretention cells because of the space constraint, and also the for roof gardens it's higher to maintain them for the rest of the year in this arid climate, because we get around 10 days of rainfall, and it's a lot of cost to keep them maintained for the rest of the time. So thank you for your patience and listening to this presentation, and I hope you have a good day and happy holidays. Thank you.